One of the really cool things that we can do now that we know a little bit more about work is we can relate it to this idea of power. And that's super useful for us in this very mechanically, electrically driven world. So power is really just the ability to do a given amount of work in a certain amount of time. So sometimes you'll see it like power, which we usually represent with just the capital letter P. Power is just the ability to do some amount of work in some amount of time. So you'll see it sometimes as this like differential. And as we know, as we've been working with work, we know that we had an equation relating this work and our forces and R, right? We had an equation that said our du for our work is the dot product of our force and dr, right? Our force vector and then that position vector dr. So we can also substitute this into this power relationship where we get the force dot product with dr t. And of course, we know from the very beginning of this class, dr dt is just a velocity. So we can get this power relationship where power is the dot product of force and velocity. And so this really can unlock a whole lot of different applications. We can relate it to motors. We can now start doing even more problems related to power, work, force, acceleration, position, velocity. All of these together, we can relate with this power. So power, we can use this du dt, or we can use force dot product with velocity. A quick note on units on power here. Our units for power in our SI unit, what we're going to see is watts. So a watt is the standard unit. We'll usually see that with a capital W. A watt is the standard unit of power, which is the same thing as a joule per second, right? That work per time. And in our US units, even though sometimes you'll see watts on like light bulbs and things, the much more common rating of power that we see is what we call horsepower. Horsepower, which I'm sure you've heard before. You might see your car engine tells you how many horsepower it is. Your lawnmower might say it's a 3 horsepower motor. And this is often abbreviated as HP. So horsepower. And the really important thing to note about horsepower is that it has a kind of weird conversion between our like standard US units and the horsepower unit. And that is that 1 horsepower is 550 foot-pounds per second, right? So foot-pounds being the unit of work in US units, and then per time. So that 550 foot-pounds per second, usually we're going to have to convert horsepower into our foot-pounds per second before we can really work with it in our equations. And then horsepower is usually the thing it gets rated at, the thing that it's sold as, marketed as, and the like conventional unit that we have in customary US unit. And we can also shortcut, if we need to, converting between watts and HP, if we ever needed to convert between our SI units and our US units. 1 horsepower is 746 watts. So those are just some handy conversions that may come in helpful when we're working through these problems, now accounting for power. And along with power, something that we often talk about is efficiency. Because usually all of the work that you put into something, all of the power, all of the energy that you put into something, you're not always getting 100% out of it. Usually, some of the work will be lost to heat. Some of it may just be mechanical inefficiencies. Lots of different reasons that it may not be a 1-to-1 ratio of energy you're putting in to energy you're putting out. And so this relationship is called efficiency. Efficiency Efficiency is this ratio of the useful power output to the power input. And the letter that you'll often see with it is the Greek letter epsilon, or sometimes you'll also see the Greek letter eta. And wow, that's a terrible looking version of that letter. Let me try that again. The Greek letter eta, it looks kind of like a fancy N. There we go, that looks much better. You'll see it as epsilon, or you might see it as the Greek letter eta. Either of those are pretty standard for efficiency. I think this book that we're using does use this eta, well, or not this eta, this epsilon. So I'll use that. But again, it's just the ratio of the power output to the power input. To the power input. And it's pretty much always going to be less than 1. For any mechanical action, any motor, anything, efficiency is going to be less than 1. Only in a perfect world would efficiency ever be exactly 1. And we don't get to live in a perfect world, so our efficiency is always going to be less than 1. Our efficiency is always, always, always going to be less than 1. You can never put out more work than you put in. So we're going to kind of use these concepts of power along with this concept of work and velocity, force, power, acceleration, all of these equations of motion, F equals ma, energy equations, all of these together with this concept of power to kind of unlock some new ways of solving equations and solving problems. So let's go ahead and take a look at a couple of examples. In this first example, we're trying to find this angle that our Jeep can travel up. So we have a Jeep, it has a weight of 2,500 pounds and an engine which transmits a power of 100 HP to all of the wheels, assuming the wheels do not slip on the ground, as in it's not rolling down, there's no friction there. Determine the angle theta of the largest incline the Jeep can climb at a constant speed of v equals 30 feet per second. I know that it can feel really overwhelming with all of these words a lot of times, but if you just remember, always use your free body diagrams, always break it down, figure out what the thing you're trying to find is, and then maybe some equations that can help you get there. Right, so like our F equals ma is usually a reliable one, and in this case we have this new power, right? We have this power, we have a constant velocity, and we know that our power is force times velocity, so that's an indication that that may be a good equation to use as well. But before we do anything, it's always our best interest, our best practice to do a free body diagram. It'll really, really help you visualize, really help you understand what's going in the problem and what we need to solve for. So I'm going to draw my free body diagram of this Jeep, and I'm going to make it just a little box because, as we can see, I didn't do that well drawing the Jeep the first time, so I don't think anybody wants to see me try that again. So we'll just have our little box on the incline there. And our Jeep, it has a weight. It gave us a weight of 2,500 pounds. And then what else do we have going on? We have the force that's propelling it forward, right? That keeps it moving forward. That force between the tires and the road so that it can have traction to roll forward. And then we have the normal force between those tires and the road there. Keeps the Jeep from falling through the earth. And then this is our angle theta. So now remember, we can reorient this free body diagram so that our x and y don't have to be this conventional x, y as we usually see it. We can rotate our x and y so that x is in line with our surface, our incline there, and then y is in the normal direction. And so when we do that, what we get is we get this little line that kind of spurts out from the normal direction, and then this angle, a little hard to see how I've drawn it. Let me just, there we go. This angle here is the same theta, right? So we had rotated at 90 degrees. So that same rotation of theta occurs up here for our 2,500 pounds if we wanted to use this like rotated axis system. All right, so now we've got a handy little free body diagram. Let's pick out what other good information this problem had for us. So we had the weight of 2,500 pounds. We put that on our free body diagram. It transmits a power of 100 HP. You know, the power is 100 horsepower. All of the wheels. Assuming the wheels do not slip, determine the angle theta of the largest incline it can climb when V equals 30 feet per second. So when I look at all of this actually written out, it feels a lot more clear. Oh, if I want to find that angle, what I can do is I can use this E equals FV relationship, see where I can relate that angle into the F, because I'm given this P and this V. If I can relate that angle into that F force there, then I can find my angle theta. So I don't know what this F is. This is really the thing that I need to find. So your F, in our case here, our F is going to be the F that is propelling it forward. The one that goes with the velocity is going to be this same F. So this guy right here, this F is the same F that goes into this equation. Our power equals force times velocity. So now we might think, okay, what are some ways that I can find that force? How can I find F? And one of the things that we can do is we can use our equation of motion, right? Our summation of F equals ma. Go ahead and try that and see if that gets us anywhere. So if I do my summation of F equals ma, and I'm going to do it in the x direction of this like rotated, this rotated axis that we have here. Summation of fx equals max. Then I'm going to have my x forces. I have the F force. And then minus the x component of this 2,500 pound force, right? So this x component here of that 2,500 pound force. So this is where I can get the angle in here, right? This 2,500 pounds times sine theta. It's the x component of the weight. Equals mass times my acceleration in the x direction. So mass times my acceleration in the x direction. But we remember that our acceleration in the x direction was basically given to us because we're moving at a constant speed. And that constant speed means that our acceleration is 0 in our x direction. We're not accelerating at all, so this is really just a statics problem. Right, we have our F equals ma, it's actually our sum of forces equals 0, and we can solve that and get that F equals 2,500 sine theta. So now I'm going to go ahead and I'm going to put this back into that power equation. Right, I have my power, I have my velocity, I have my F in terms of theta so that I can solve for that theta. The only thing that I really want to make sure and pay attention to is my units here. Right, I have this power in terms of horsepower. So I want to convert that into my foot-pounds per second before I move forward with this so that I don't have any errors in calculation from a conversion error. So I know 100 horsepower, or I should say I know 1 horsepower is 550 pound-feet per second. So that means that my 100 horsepower is going to be 55,000 foot-pounds per second. So this is the value that I'll plug in into my P down here. So I have 55,000 foot-pound per second equals my force, which is in pounds. I had 2,500 pounds, 2,500 sine theta times the velocity of 30 feet per second. And so if I do a little bit of rearranging here, I can multiply this out. 55,000 divided by, let's see, 2,500 times 30 is 75,000. So divide over the 75,000. And then I can take my inverse sine to find that angle theta. An inverse sine to find that angle theta. And I get from my calculator an angle of 47.2 degrees. So my Jeep, when it's traveling at a constant speed of that 30 feet per second, it can climb up a hill of 47.2 degrees without slipping, which is pretty impressive. I guess that's why the car dealerships always have their Jeeps like mounted up on their little like weird little triangle showcase things. You know what I'm talking about? Where they have them like sitting on the corners and they're on these impossible rocks. I guess the Jeeps are really capable of that. Anyways, let's do one more problem. Let's take a look at one more example, and this time we'll incorporate the idea of efficiency along with our power. So in this example, we have a sports car that has a mass of 2.3 megagrams, and while it's traveling at 28 meters per second, the driver causes it to accelerate at 5 meters per second squared. The drag resistance on the car due to wind is Fd is 0.3 v squared newtons, where velocity is in meter per second. Determine the power supplied to the engine at this instant. Our engine has a running efficiency of 0.68. So again, a lot of information to digest. So let's go ahead and do a free body diagram, write out what we're given, and see what we can work out from there. So again, I'm going to stick with my little box for the car. And I can see that my car, of course, it has that mass of 2.3 megagrams. So I know that my car has a weight. And because my car is on the road, it has that normal force from the road pushing back up on it. I can also see that drag resistance, right, which we can kind of see is those little light blue lines kind of going over the car. That wind due to drag resistance they give us is Fd is 0.3 v squared newton. So that Fd is 0.3 v squared. And then of course there's the force that is propelling this car forward, right? The interaction of the tires on the road that move it forward, that force, and I'm just going to call that F. No friction or anything else, so this is going to be our complete free body diagram. And let's see what we didn't pull out from our big text box at the top here. So we had mass of 2.3 megagrams. Again, a megagram, that is 10 to the 6th grams. So 2.3 megagrams would be 2,300 kilograms. So the weight being 2,300 kilograms times gravity, 9.81. While it's traveling at 28 meters per second. So our initial velocity is 28 meters per second, and the driver is accelerating at that time 5 meters per second squared. They give us Fd, and they say determine the power supplied to the engine at this instant if there's a running efficiency of 0.68. So our efficiency is 0.68, and we're trying to find our power supplied to the engine. So power supplied to the engine is the power that is going in. The power that is going out is the one that is actually causing the force, like it has to deal with the actual forces that are happening on the body. So in order for that force to like move the car forward, it's the power output that is related to that actual force of movement, not the power input. So the power input we'll actually find by this efficiency relationship, whereas the power output, that's going to come from our P equals F times V. So we're looking for our power input. Input is what we're trying to find. So given everything that we have here, we know we're going to want to find a power. So we might as well put our power equation down here. Power, and again, this is the power out, is going to be our F times V. But we don't know what F is. So we're going to need to find that F from our summation of forces. Okay, from our summation of forces, we're going to want to find the net force that's acting on this car. So our summation of forces in the x direction, because that's our direction of velocity, that's our direction of movement here, is going to be our F minus FD, which is 0.3 V squared, and that equals MA. Let me rewrite this. Let's move this down here. This is our FX term. Really, our sum of FX equals M times AX. So our sum of FX, that's our F force from our diagram minus the drag force, right? Drag is pushing back on that car, equals the mass of the car, 2,300 kilograms, times the acceleration of the car. And that was another given, that was 5 meters per second squared. So this gives me that the force for our power calculation is going to be 0.3 V squared plus 11,500. 11,500. So I'm going to take this and I'm going to use it in my power output. So my power output is F times V. So it's going to be my F, 0.3 V squared plus 11,500 times velocity, and our velocity at this time is 28, which I also need to substitute in right here in my equation as well. 0.3 times 28 squared plus 11,500 all times 28. So that gives me a power output of 328,590 watts, right? Everything I had converted into standard SI units, which means that the units that I get out are going to be watts. So now that I know the power output, I can use my efficiency relationship to find that power input. So efficiency is our power output over our power input. So if I rearrange this, I get my power input is the power out over my efficiency. So that's 328, let's say 328.59 kilowatts over the efficiency of 0.68. Which gives me, from my calculator, a power in of about 438 kilowatts. 438 kilowatts. So I had to put more power in than was actually required, than the power out, to get this movement of the force, right? Because of that efficiency relationship. So we can use this power to work with, machinery, things that have to deal with motors, to calculate our forces, velocities, and anything that we might need to related to these equations of motion, kinematic, and kinetic problems.